How can we make real-world graphs more well-connected and robust? In this work, we studied the problem of improving the cohesiveness of graphs by merging nodes. The presentation will cover the following contents. We will first provide the background of this work. Then we will cover the three aspects: formulation, analysis, algorithms. After that, we would like to show some experimental results. Finally, we will conclude our presentation by summarizing our work. First, let us provide some background. What are graphs? A graph is mathematically defined by its nodes and edges, where edges represent binary relations. Graphs can be seen everywhere in real world. Such relations can be between real-world objects. For example, on maps, edges can represent roads between two locations. There are also graphs describing relations between people, like social networks. Then, what do we mean by the cohesiveness of graphs? The Cambridge English Dictionary defines cohesive as united and working together effectively. It sounds very nice, isn't it? Cohesive graphs intuitively mean dense and well-connected graphs. In the example below, starting from a graph without any edges, as the number of edges increases, the graph becomes more and more cohesive. We have a high-level understanding of cohesiveness now. But why do we want to make graphs more cohesive? You know what? We actually love cohesive graphs in real world. In many real-world scenarios, we want the network to be cohesive. In other words, well-connected and robust. For example, cohesive public traffic networks implies that the routes are convenient and they can still function properly even when some problems happen. Also, cohesive social networks imply good communication and tight interpersonal relations between members. We have just provided some background, and we now know why improving the cohesiveness of graphs is an important and realistic problem. But how can we formulate such a problem mathematically? Specifically, what operation and what metric do we consider in our formulation? Let us first look at what researchers have considered for such a problem. As we can see, two popular cohesive subgraph models are frequently used, while the operations are either anchoring nodes, that is, forcing nodes to stay in the cohesive subgraph, or adding edges. However, another realistic and interesting operation has been overlooked, which is the operation of merging nodes. In public traffic networks, merging nodes can make the whole network more compact and can reduce maintenance expenses. In social networks, merging nodes can represent forming teams, which can create a more collaborative and a synergic environment. We picked the model of K-Trusses to measure graph cohesiveness. Given K, the K-Truss of graph is a maximal subgraph where each edge is contained in at least K triangles. Compared to the concept of K-Course, which only considers node engagements, the concept of K-Trusses further involves edge interrelatedness. K-Trusses also have other desirable theoretical properties, such as bounded diameter. We provide an example here, starting from the highest K equals 5, which implies the highest cohesiveness and the tightest condition. When we reduce the value of K, we have a larger and larger range, while the cohesiveness also gradually decreases. Until we reach K equals 2, which gives the whole graph. We define the trustness of a node or an edge as the maximal K such that this node or edge is contained in the K-Truss. On top of desirable theoretical properties, K-trusses are also practically meaningful. Intuitively, the concept of K-trusses involves triangles, which can increase connectivity and the robustness of graphs. When we have a triangle, even if one of the three connections fails, we can still have a well-connected structure. But if we do not have a triangle, then the failure of a single edge will be fatal. We have more discussion on why the concept of K-Truss is suitable in our paper, especially why it's more suitable than the concept of K-Course. Also, we can see here how forming triangles can increase node degrees and reduce the diameter of the graph. To conclude, we consider the problem of maximizing the size of K-Truss by merging nodes. Here we provide the formal problem statement. We are given a graph, trussness K and the budget B. We aim to find B pairs of nodes to be merged so that the size, or more specifically the number of edges in the K-Truss after merging its pairs, can be maximized. We show an example here. We mark the trussness of each edge in this graph, and we shall see how merging different node pairs will change the trussness differently. First, let us merge nodes 2 and 4. After merging the two nodes, we can see that some edges trussness increases from 2, the red ones, to 3, blue ones. Meanwhile, some edges trussness decreases from 5, the purple ones, to 4, the green ones. Certainly, there are also some edges whose trussness stays the same. Let us try merging two different nodes, say 6 and 12. The result will be quite different. As we can see here, this time some edges trussness increases and none decreases. We have seen how merging different node pairs can bring different consequences. It's interesting yet complicated, and we will study this problem in this work. We have the formal problem statement now, and we're going to analyze the problem, and we're going to develop algorithms accordingly. First, we analyze the theoretical hardness of this problem. We prove the NP-hardness and non-modularity of the formulated problem, which implies that the problem cannot be easily solved. We aim to find practicable and efficient heuristics. Let us start with a naive algorithm, which greedily chooses and operates the best possible pairs of nodes to be merged until the budget is completely used. This is definitely doable, but time complexity is prohibitive. Each component in the time complexity corresponds to one process in the naive algorithm, and you can see the correspondence indicated by colors. How can we reduce the time complexity? An idea would be reducing the B-square part by identifying less promising mergers and promising mergers. Here we give the overview of the proposed method. First, we find promising nodes that might constitute good node pairs to be merged. Then we further find promising node pairs between the chosen good nodes. After choosing the node pairs, we evaluate each of them and pick the best one. We repeat the above process until the budget is completely used. Let us introduce some technical details. First, we analyze the changes after a single merger so that we can evaluate nodes or node pairs more easily. We first found out that when we merge two nodes, for all the edges that are not incident to either of those two nodes, the trussness changes by at most 1. This implies that When we consider the consequences of a single merger, the potential new K-Truss after the merger is within the range of the current K-1 truss plus edges incident to the merged nodes. We also found that when we merge the nodes for the edges whose current trussness is higher than that of at least one of the merged nodes, the trussness will not decrease after the merger. Specifically, if at least one of the merged nodes is in the current K-1 truss, then the current K-truss will not receive any damage after the merger. In other words, we don't need to worry about the situation that some edges in the current K-truss leave it. The two lemmas together can help us reduce the number of edges we need to check after the merger. Lemma 2 also shows us that the nodes with current trussness at least K-1 have spatial importance. Therefore, we would like to pay special attention to those nodes. We also give special names to them by the following definitions. We have an example here in the picture. This node Vi is an inside node, and this node Vo is an outside node. And for this node U, Vi is its inside neighbor, because Vi is an inside node and it's a neighbor of U. We can easily compare two outside nodes by their inside neighbors. Lemma 3 tells us that we can only consider outside nodes with maximal sets of inside neighbors. In other words, no other outside nodes have a set of inside neighbors that is a strict superset of them. But how can we efficiently find such outside nodes? Let us first see an example here. Because the inside neighbors of U1 is only this Vi1, while the inside neighbors of U2 are both Vi1 and Vi2. For any node V, by lemma 3, merging V and U2 would be better than merging V and U1. Note that we have no requirement on V, and this has nothing to do with U1 and U2's neighbors outside the current K-1 truss. The problem is essentially finding maximal sets among a collection of sets, which is a well-studied problem. We thus utilize an existing simple yet practical algorithm which runs in a reasonable time. Now we know how to find good outside nodes, but that technique does not apply to inside nodes. How can we find good inside nodes? We aim to find a good heuristic for it. We first give the definition of incident prospects here. Again, let us see an example. Here we have three neighbors of the node V, where only Vi1 counts as an incident prospect of V, while Vo's trussness is too low and Vi2's trussness is too high. Again, only neighbors with trussness exactly K-1 are counted as IPs. The intuition is that the IPs of a node V approximately corresponds to the edges incident to V that are not currently in, but well possibly in the K-Truss. And therefore we will use the number of IPs as the metric to choose good inside nodes. Now we know how to find good outside nodes and good inside nodes, but we may still have a large number of candidate mergers involving those nodes. For further analyzing the mergers, we first divide the mergers into three categories based on whether the involved nodes are inside nodes or outside nodes. Here we have two outside nodes and two inside nodes. If we merge two inside nodes, Vi1 and Vi2, it will be a so-called inside-inside merger. If we merge two outside nodes, VO1 and VO2 here, it will be an outside-outside merger. And similarly, if we merge one inside node, say VI1, and one outside node, say VO1, that will be an inside-outside merger. We claim that mergers between two outside nodes, in other words, the so-called outside-outside mergers, are unlikely to be helpful, and we thus exclude all of them. Notably, OOMs usually have the highest number among the three kinds of mergers. For the remaining two categories, we use some score functions to rank them. Indeed, in the example when we introduced the problem statement, we have seen how mergers can bring both positive and negative consequences with regard to trustness. The score functions of a merger contain both positive parts, contributed by the edges that are contained in new triangles after a merger, and negative parts too, since mergers can also make some edges collide or lose support. In other words, some triangles containing the edges are destroyed. After taking both sides into consideration, overall, we will see the mergers with the highest scores as the most promising ones. Now we're going to show some experimental results. We use 14 real-world graphs in various sizes. We also consider different k-values. Since we are the first to consider the problem, we use several other heuristic-based methods as our baseline methods. Here are some basic statistics of the datasets used in our experiments. We can see that datasets vary in sizes and other statistics. Here on each dataset, we show the performance of each considered method, averaged over or considered k-values. We can see that the proposed method, the so-called BM here, consistently outperforms the baseline method. We will not cover the details of the variance here, but briefly speaking, those variants lack a budget distributing component and thus perform less stably compared to the full-fledged proposed method. We also compare the methods when some parameters change, such as different budgets are given, different k-values are used, or we are allowed to check different number of mergers in each round. As shown by the results, the proposed method still consistently outperforms the baseline methods, while performs more stably by its variance. Regarding the speed indicated by the running time, we can see that the proposed method uses slightly more time than the simple baselines. But more importantly, on the right side, we can see that the proposed method achieves the best trade-off between the running time and the performance. Let us conclude our presentation. In this presentation, we covered the formulation, the analysis, and the algorithms regarding the problem of improving the cohesiveness of graphs by merging nodes. The experiments on real-world graphs show the efficiency and the effectiveness of the proposed method. This is the end of our presentation. Please check out our paper and code available online for more details. And feel free to contact us if you want to have more discussions. Thank you for your attention.